So we've been talking about this differential equation here, which I've told you we can use to model the proportion of an activated amount of protein over the total amount of that protein. And that can be interesting to us because we can think of an ion channel as being open or activated or closed, and switching between these two different states with constants alpha and beta. So in this video, I want to pick up where we left off. So when we left off, I said that we could re-express this equation in this form, and this is nice because it explicitly tells us what the steady state value of x is going to be. So x will approach a steady state if alpha and beta remain constant, which we are assuming for now at least. And xss we found was equal to this, and we had this other term that ended up here, and I called this the time constant. And the reason it's called the time constant is because it scales the dynamics of the system but does not affect where x approaches steady state. So in this video, I'm going to solve this equation here in the same way that I solved the original equation for exponential decay by separating variables. So the way this works is divide both sides by xss minus x, multiply both sides by dt, and divide both sides by tau. Okay, now I'm going to integrate both sides because all my x variables are on the left side and all my t variables are on my right. So the integral of this, you have to remember the chain rule, so there's a negative that comes out up front. Negative natural log of xss minus x. This equals, so 1 over tau is just the constant, so integral of dt is just t, so we have t divided by tau plus some constant of integration, which comes from, the two integrations that we did, and we just combine them on the right side. Okay, so the next step is to multiply both sides by -1 and exponentiate, and that gives us xss minus x equals e to the negative t divided by tau plus c. And then the last step is to isolate x of t. I'm going to bring the c down in front of the e because of our properties of exponents. We've seen that before. So we have xss minus c e to the negative t over tau. One thing that might be confusing to some of you is why I'm still calling this c even though I'm bringing it down to the front. So this is, if this was c1, then this c here would be equal to e to the c1. And the reason I'm doing this is because I don't really care what the values of any of these constants of integration are. I'm just going to, they're just some constant, and at the end I will put it in terms of the initial condition, which is the next step. So I'm just calling them all c because, I don't really care about them. I don't really care what they mean. So to finalize this, we plug in the initial condition. And we'll call the initial condition x0 so that we can be flexible. It's just a constant. It's the value of x, or the proportion of activated protein at time 0. So at time 0, this equation becomes xss minus c because when t equals 0, this goes to 1 because e to the 0 is 1. Okay, so this then implies the following: c equals xss minus x 0. Okay, so now we have the constant, which we've put in terms of the initial condition, so that's going to go there. So I'm just going to quickly erase all this stuff and rewrite this equation at the top of the screen. Alright, so x of t equals xss minus, and we're going to plug in our value of c here, which is xss minus x0 times e to the negative t divided by tau. Okay, so this is pretty much it for this video. We have this final result, which tells us exactly how x is going to evolve over time. And I just want to quickly give you a little bit of intuition about what this equation is telling us. So we can see that as t approaches infinity, then this term here will approach 0. because this exponential here is going to approach 0. And that means that x is going to approach the steady state value of x. So that makes complete sense. Okay, so that's a good intuition that, that makes sense to us. Now, what happens when t equals 0? Well, when t equals 0, then this term here is equal to 1, and that would mean that these two terms, xss, are going to cancel. And negative times negative, we are just left with x0. So at time 0, we have our initial condition, and that's pretty important. If that wasn't the case, we would have an issue. Okay, so this equation is making sense to us so far. Now I'm just going to quickly plot what this looks like. So if this is the horizontal axis is time, vertical axis is our dynamic variable x. And I will mark the steady state as some value here. And just to remind you, x has to be between 0 and 1. So I guess we could put those hard limits on this axis if we wished. Okay, and now I'm going to draw different trajectories. So let's say I'll pick a value of x0 here. So this would mean that in the initial condition, we don't have a lot of activated protein for whatever reason. And then we're going to start activating it because alpha and beta are constant, and they give us this XSS, which, again, you can find by this equation here. So if this is our initial condition, what is our solution going to look like? Well, our solution is going to exponentially approach this steady state value. And we'll never quite get there, but it'll asymptotically approach it. And that makes sense, right? Because you have this exponential term, and over time, this term is decaying away, so you're only left with XSS. And since x0, in this case down here, is less than XSS, then x of dx dt is positive, if you think about it there. So dx dt is positive, and will approach the steady state value. Okay, and then I'll just draw one more trajectory on here. Let's say we had a different x0 up here. So this is just like another experiment where our initial condition is now higher than XSS. What's going to happen here? Well, essentially the same thing. We're going to exponentially approach our steady state value. And from that intuition, you should be able to figure out, okay, well, if I started here, we'll get some trajectory that looks like this, and if we start down here, we'll get some trajectory, sort of looks like that. And all of our trajectories are approaching this steady state value exponentially. And the time constant, which I will talk about more in the future, I guess, the time constant sets how quickly these trajectories approach steady state. So if the time constant was higher, if the time constant was smaller, then you would get trajectories that look like this, that would approach steady state more quickly. So that's just a little preview of what we will talk about in the next video. Thanks.